Thank you for introducing me, and thank all of the organizers for inviting me here. Nice workshop, and giving me a chance to talk here. And my title is the formula for the real Buchstaber invariants of special simplex, skeleta of a simplex. And the outline of my talk is here. I'll introduce the definition of Buchstaber invariance, and to calculate that invariance for some special simplicial complex K here, the n-p-1 skeleta of n-1 simplex, and I'll calculate the real Buchstaber invariance of them. To find them, I'll introduce some special integer linear programming. And I'll give you the solution of that ILP. And finally, I'll talk about some periodicity of them. K is abstract simplicial complex. As mentioned, for many speakers talked about that. ZK is moment angle complex, and RZK is a real moment angle complex. And naturally, there on ZK, there is a natural TM action on them. And that action is not free in general, so we can define Buchstaber invariance like Buchstaber invariant as K is the maximal dimension of the subtorus TM acting freely on the moment angle complex. And similarly, we can define real Buchstaber invariance. SRK is the maximal rank of C to M acting freely on RZK. These three facts are very well-known facts. Buchstaber invariance is bounded by n-n, and real Buchstaber invariance is greater than or equals to original Buchstaber invariance. And if K has if K has Buchstaber invariance with P, in case of P is 1 or 2 or 3, then Buchstaber invariance is the same as the real Buchstaber invariance.
There only if P is 3.
Yes. No, sorry. It's my mistake. No, 3. 1 or 2. Yes, you're right. You're right. I'm sorry. Yeah. And there are many directions of the research, but I will introduce some of them. Buchstaber invariance is maximum for n-n case, so find an effective criterion for S of k is n-n is important. And second, we want to know the behavior of Buchstaber number under some operation and construction on k. There are many constructions and operations we can think about. And some relation between Buchstaber invariance and classical combinatorial invariance, like chromatic number, F vectors, and so on. And find a Buchstaber number for special class of simplicial complex and polytopes. And generally, we want to describe the class of simplicial complex and polytopes with given Buchstaber invariance. And my contribution to this talk is about this special simplex complex. And generally, Buchstaber number is bounded by upper and lower. Lower bound is m is the number of vertices of K, m minus chromatic number of K plus some Buchstaber number of skeleta of a simplex. And upper bound is m minus log 2 of something. So it has a meaning to consider the Buchstaber number of skeleta of simplex. In 2010, Fukugawa and Masuda have some research about real Buchstaber number of skeleta of simplex. There is a set of numbers mk of b such that m minus p minus 1 skeleta of m minus 1 simplex have real Buchstaber number greater than or equals to k if and only if m is less than or equals to mk of p minus 1. And this number mk of b is obtained by some integer linear programming. I will introduce integer linear programming later. And they have some research. First, k equals to 2 case. If k is 2, then real Buchstaber number of this is greater than or equals to 2 if and only if m is less than or equals to 3 times p minus 1. And they found some lower and upper bound of mk of this, and they conjectured that mk of this number is 2 to the k minus 1 times q plus mk of r. And they gave a partial answer for this conjecture. That is, if p is sufficiently large, in this case, this conjecture is true. You know that this statement and the bottom line is the same statement. And as I mentioned before, this integer linear programming can be modified more fancy. A k of b is x. Maximize summation of xi. This b is such that no. Such that here A2 is 0, 1, 0, 1, 0, 0, 0, 0, 1, and AK is 1, 1, 0. And this one is the matrix for every entry is equals to 1. And the optimal solution of this integer linear programming is the same as mk of b, as defined earlier. And every integer linear programming has dual problem. It is similarly defined by this form. The inequality has changed and maximize becomes minimize. And I'll define the optimal solution of this dual problem as mk star of b. And in general, it is not easy to solve integer linear programming, but this dual problem can be solved a little bit easier. These three lemmas are key lemma to solve dual problem. And from this lemma, we get the full solution of this dual problem. And before I state this solution, I will introduce some notation. For convenience, given k greater than or equals to 2, I will rewrite any integer as this form. Here, C1 is quotient of a divided by 2 to the k minus 1 minus 1. And C2 is the quotient of the remainder divided by 2 to the k minus 2 minus 1, and so on. And I will give an example. For k is 5 case, 58 is 3 times 15 plus 7 plus 2 times 3. So it is. It can be expressed as unique form. So I rewrite 58 as 3120 bar. I will rewrite this.
Now your k is a fixed one, right?
Yes, k is fixed. Yeah. If k is 4, then the 58 can be expressed differently. Yes.
Very long.
Yes, long. Shorter. Shorter. Yeah. 58 is. Okay. Yes. And then the optimal solution of the dual problem can be written by this nice formula. But original primer problem cannot be expressed such like nice form. So we have to make some other notation. Decay of b. Consider b is between 0 and 2 to the k minus 1 minus 1. Then optimal solution, solution vector in this case, solution vector y of the dual problem, it cannot be guaranteed that y is bounded by 1, 1, 1, 1, 1. So I'll define dk of b is this. Consider all the optimal solution vector of this dual problem and take maximum of the component of the optimal solution vector and take minimum. It's hard to understand, but the meaning of this definition is here. If a is smallest number such that there exists an optimal solution vector of the dual problem satisfying this condition, then dk of b is a minus 1, vice versa. This is the meaning of the dk of b. Anyway, with using dk of b, we can we can state the formula of primer problem as this. For a and b integer with the summation of two integers is equals to 2 to the k minus 1 minus 1. And if L is greater than or equal to dk of a, then the sum of optimal solution of a primer problem and dual problem is equals to 2 to the k minus 1 times L plus 1. But we know all the solution of the dual problem, so we can deduce the solution of a primer problem by 2 to the k minus 1 times L plus 1 minus the solution of dual problem. That is stated the bottom line. And I missed some result of Fukugawa and Masuda. Their result, one of their result is SR of this is fan on it. I mentioned. Really, I mentioned. Sorry, I mentioned. So if we know the values of primer problem, then we can state this. That is here. If we rewrite p minus 1 as this kind of form, and suppose L is greater than or equals to dk of something, which depends on p minus 1, then the real Buchstaber number of skeleta of n minus 1 simplex is greater than or equals to k is if and only if this nice formula.
It means that you can compute the real Buchstaber number over those cases completely? Because CI can be computed from P.
Yes. CI is from P.
And L?
L is here.
Yeah. So then, I mean, you can compute the skeleton of simplexes
Here.
cases completely.
Not completely. This assumption here. If P is greater than or equals to some number, this formula holds. I mean, P minus 1 is plus this is here. So this condition means P minus 1 is greater than equals to some number. If if P minus 1 is some small number, then we cannot apply that formula. Right? So,
But the case for case is actually it says automatically this assumption.
Pardon?
In case
You say this is generalization of this theorem. So that can means like
Partially generalization.
yeah.
If k equals to 2, then p minus 1 is, if k is 2, p minus 1 is L plus 1. All ci's are 0. So we apply here, then summation of ci's is 0. L plus 1 is p minus 1. Then we get this formula. As Soo-young mentioned, the remaining research area is finding decay of something. Yeah. This is important.
But even if you find the decay, then it does not mean that it solves all cases.
Yes.
So you have to do something more.
Yes, something more. And before stating about decay of something, I'll introduce some notion of periodicity. How many times do I have? 15 minutes. Thank you. MK of B is the optimal solution of primer problem is pre-periodic for large values of B. I mean, pre-periodic means if some function f is pre-periodic, means it's periodic with the period t and the shift s. In MK of B case, MK of B plus t is MK of B plus s if B is large enough. In this case, period t is 2 to the k minus 1 minus 1, and the shift s is 2 to the k minus 1. And some observation here, the moment at which the behavior of MK of B becomes predictable and pre-periodic depends on the remainder of B modulo period. And this moment is encoded by the constant decay of B. And this condition is this L is greater than or equals to decay of something is just the moment at which MK of B is pre-periodic. So that means if L is less than decay of this, then MK of B is no more equals to some nice formula. MK of no more. And the meaning of periodicity of this real Buchstaber invariant of skeleta of simplex is described as follows. If we rewrite, P minus 1 can be expressed as two ways. One way is divide by 2 to the k minus 1 minus 1. And the other way is to divide p minus 1 by 2 to the k minus 1. Suppose given m and p, given p and real Buchstaber invariant is k if and only if m is bounded by a and b, then if we shift p by p plus 2 to the k minus 1 minus 1, that is period. If we shift p by a period, then it is equals to k if and only if n prime shifted by the shift s. Yeah. And this is the meaning of preperiodicity. Also, we need these two conditions. And this is an example. Note that 21 is 15 plus 6, and this number and this number is a. I used a. And anyway, these two numbers are 0, so we don't care about this condition in this case. Let k equal 5 and m equals to 40. Then if we apply the formula before, then this equals to 5 if and only if p is 21. And if we use the meaning of preperiodicity, then if S R of this skeleta of simplex is 5, if and only if p is 36. Do you see that 40 becomes 71? The gap is 31. 31 is 2 to the 5 minus 1. And the gap between 21 and 36 is 15. 15 is 2 to the 4 minus 1. Yeah. And as I mentioned before, studying decay of B is important. And let k is greater than or equals to 2 and b is positive integer, then up to now we have such kind of properties of decay of B. First one is if k is less than or equals to 4, then decay of B is 0, so we can apply the formula. If k is between 5 and 7, this number is 0 or 1. And if k is greater than or equals to 7, then it is less than or equals to k minus 6. And second property is can be applied for the case b is some big number. If k is sufficiently big, then this this property is more useful than the first property because it is k minus something divided by 2. And if b is between these two numbers, then decay of b is 0. And finally, if b is b satisfies some condition n times k, then decay of b is n minus 1. Sorry. This is less than equals to n minus 1. And this is my last slide. Thank you.